Okay. Welcome. If you want, you can share your screen, Michele.
Okay, just trying to do that. I don't know if
Okay.
can you see my screen?
Okay, we can see. Yes. Okay.
But sorry if asking. I a couple of screens. So you're looking at the presentation right now.
Sorry, we can't hear you well at the moment.
Can you hear me?
Not like before. Maybe you have some troubles with your microphone.
Can you hear me?
Not a lot.
Meaning that you don't hear me because like it's cracking or it's
Maybe there is some problem with your microphone because here. Okay, so okay, one moment.
yes.
Let me try to do one thing. Okay. Okay, try now.
Can you hear me?
Okay, now yes.
That's
Okay.
great. And are you seeing my screen sharing from my slides?
Yes.
That's great. Just last question. Would you like that I activate my video?
No,
It's
it is not required, I think. No, no problem.
okay. No, it's just I can do it.
Okay, if you want, it's your choice.
Okay.
Okay, so welcome everybody to this AJS. Sorry for the beginning. It's been a pleasure to introduce you the speaker of today, Michele Errante. Michele Errante was or is still a PhD student at Politecnico of Turin, but it has joined at ANSYS, work in the research and development group at ANSYS at Munich. And today it will cover arguments strictly connected to turbulence modeling. That is mixed. His talk is entitled Mixed Averaging Procedures. So Michele, please.
Yes. Well, hi everyone, and first of all, I would like to say thank you to Nicola and Guglielmo for the kind invitation. Really, I'm really happy to be here today, and I think this seminar series organized by young researchers for other young researchers is a great opportunity to exchange ideas and stay updated on what's happening around us and building a network. So I'm really glad to be part of it, and I hope you will enjoy the talk. I will try to stay as much as informal possible. Just a brief introduction about my background. I think it's correct for the audience. I studied aerospace engineering at Politecnico di Torino, where I also had my PhD, and my research focused on numerical simulation of turbulent flows in aerospace propulsion systems. And now, as you mentioned, for a little over 2 weeks, I started a new exciting adventure at ANSYS as an research and development engineer in CFD. And actually, I take this opportunity to thank my new colleagues for allowing me to take part in this seminar during work hours. And of course, the content of today's presentation is part of the work I carried out during my PhD at Politecnico di Torino. And I also want to emphasize that this is not an individual effort. So this work was made possible thanks to the collaboration of several professors, who I'd like to mention and thank. They are Professor Markus Klein from University of Bundeswehr Munich, Andrea Ferrero and Francesco La Rocca from Politecnico di Torino, and Guglielmo Scovazzi along with Massimo Germano from Duke University. So today we are going to talk about turbulence, and as we all know, numerical simulations of coarse-grained turbulence, meaning basically all numerical simulations with exception of DNS, direct numerical simulations, rely on two fundamental components, which are we have the filtering operator, which defines the level of coarseness in the representation. So here we have runs LES, hybrid runs LES, but during today's talk, we will not focus on that. Let's assume that we have already run our simulations with a given filtering operator, but we still have a problem because we have data, which for turbulent flows are chaotic. So we need statistical operators which extract meaningful quantities from the chaotic computational data that we have. So, well, the ideal statistical operator will be, of course, ensemble average, and in particular, as Professor Germano likes to call, an old dream, a practical realization of ensemble averaging in real turbulent simulations. So just a definition, given a generic function f of space, time, and the particular realization, the statistical operator curly En for the ensemble average is expressed through the summation of f across the capital N realizations indexed here by alpha. So here N is the number of realization and alpha represent different realizations. So okay, so straightforward. But the theory of turbulence is primarily based on the concept of ensemble averaging, and the statistical description of turbulent flows largely depends on that. However, we have a problem. Simulating turbulent flows using only ensemble average is still a long way off because it will require an affordable computational cost. So time, space, or phase averages are the usual surrogates, acting as substitutes in a way for ensemble averages when possible. And here are the definition, curly ET here of f is given by the integral of f in time over the time interval curly t, and curly E of f is given by the integral of f in time over the time interval over the dimensional space y. In this case, we have y as dimension as dimensional direction, and then we have also the phase average, which is given by the integral of f between 0 and 2 pi over 2 pi. So just a note, there is a consensus in the belief that turbulent flows are ergodic in the sense that asymptotic space and time averages and ensemble statistical means should be the same, but till now there seems to exist no direct evidence regarding the validity of the ergodicity hypothesis in turbulent flows. Another way is using mixed averaging procedures, which are currently applied as substitutes of the ensemble averages, in particular simulation of steady turbulent flows, which are provided with homogeneous, for sure, by definition, symmetries. And in particular, mixed ensemble and time or space or phase averages are currently applied in complicated geometries and complex problems in literature. So let's delve into how we estimate expected values using mixed averaging. So we can define a statistical operator, which is denoted here by curly E, as the product of two or more averaging operators. So here the subscripts I, which are 1, 2, 3, refer to averages in time, in homogeneous direction, ensemble solutions. I mean, meaning it could be one of the homogeneous direction. So in this case here, for example, we focus on a mixed averaging approach on ensemble averaging with time average. So we have already defined curly ET and curly EN. So basically, at the end, this new statistical operator, which is the averaging, the mixed averaging statistical operator, is simply the products of curly ET and curly EN. And I just, at the bottom of the slide, included some references to some insightful studies using this mixed averaging approach. Or another example, here we have a mixed averaging approach in time and space. So curly E this time, the mixed averaging statistical operator is given by the product of time average curly ET and curly EY. And as for the previous slide, I included some papers which implemented this mixed averaging post-processing procedure to some, let's say, interesting test cases. So until now, we have just defined statistical operators. And we know, unfortunately, that testing statistical convergence is not so simple, both from the theoretical and the practical point of view. So the usual way to do this, to test the asymptotic convergence of space and time averages is the analysis of, let's say, when we have to analyze steady turbulent flows, we compute the correlation times and correlation lengths in the homogeneous direction. But this is not always easy. However, various algorithms have been proposed to estimate the variance of the computed averages fields in order to assess the statistical convergence of results. Noteworthy here, I put these methodologies like the non-overlapping batch means method, the overlapping batch means method, and batch means batch correlations, so it's BMBC method. So basically, we divide time, the total time of simulation in batches. For let's say for the first method, and these batches are not overlapping, and then we compute the average of each batch, and then we use the variance among these averages for estimating uncertainty. Or let's say the last one combines the computation of the batch averages with let's say the correlation among the batch themselves, and it's we need that for correcting errors that are introduced by the temporal dependence among data, because of course they can be correlated. But apart from the details, these approaches, while distinct, share a fundamental conceptual similarity, requiring the delimitation of subsamples. So these batches derive from the let's say computed time history that we have. So those approach and do not address the relative, let's say, if we have mixed averaging procedures, then they don't address the relative importance of the different averaging procedures that we have inside, which actually is the focus of the present presentation of the present talk. Because what would we like? Actually, we would like to evaluate the, as I said, the relative importance of averages in mixed averaging operators. And we would like to do that, let's say, using and computing metrics that are straightforward and easy to implement in principle. So let's consider turbulent flows that exhibit homogeneity in both time and in span-wise, direction-wise. So this is the class of problems that we want to tackle. So we define U high which is the components of the velocity fields, and of course it is function of time and space. So the statistical average curly E of Uy is given by the following definitions. They are the same as the previous slides. We just applied here from a generic function to, in this case, to the components of the velocity field. So we have here the average in time, we have here the average in space, and then we have the curly E, which is the mixed averaging statistical operator, which is the product of the two. So the idea now, so again, we want to arrive to defining some metrics that are very easy to understand and to access, also to compute, and then give us the let's say relative importance to the statistics. So the idea comes from Professor Germano, which suggested to pass through an operational decomposition of the variance. So if we introduce here the generalized central moments, mainly we can quantify the variance and correlation of turbulent fluctuations after applying different averaging operators. So the first question represents the variance of velocity components Uy and Uj, let's say after time averaging. So this measures how much turbulent fluctuations remain after time averaging. The second equation here represents, again, the same thing, but for the span-wise averaging. The third one, we have, let's say, bracket of brackets. So this represents the variance of the span-wise averaged velocity fields after we apply time average. And the way around the fourth equation, we here represent the variance of the time average velocity field after, so it was averaged in the span-wise direction. So at the end of the slide, so the last equation represents the total variance, basically. So the variance of the fully averaged velocity field, where averaging is first done in time and then in Y, or vice versa, because it is identical. For this reason, we have this double equality. So it is easy to see that in terms of these quantities, we can express the following identities for tau ty, which is equal to tau yt. So the meaning of this decomposition here of basically the total turbulent stresses, because here we recognize the Reynolds stress, it's basically found in the statistical law of the total variance. So basically, again, as I said, here we have tau ty, and which is equal to the Reynolds stress, and then the components of each equations, in reading them, let's say, with the statistical law of the total variance, are the fractions of the Reynolds stress due to the time averaging within and between the space average. So here in the first identity, in the second identity, we have the fractions of the Reynolds stress due to the space averaging within and between the time average this time. So basically, how much time averaging and how much averaging in Y, so in this span-wise direction, each contribute to capturing better the variance, so the Reynolds stresses. So in particular, here we want to, because we can do that, and it's very easy, we can use those tau ty and tau yt to y high and to u high and u high. So basically we are using here the Reynolds stress trace, which represents the turbulent kinetic energy associated with it. So basically to extract a scalar measure of how much the operators tau t and tau y contribute to the variance. And the introduced indices provide a computational, let's say, straightforward and physical intuitive method for assessing the efficiency of mixed averaging procedures among the different averaging components. Because here, for instance, MT, which is function of X and Z, is a quantity for how we define that, which is ranging from 0 to 1, that indicates that fraction of turbulent energy, which is captured or let's say explained by averaging in time. So if MT is almost equal to 1, and on the other way around, My is approaching 0, it means that varying time alone is sufficient to capture almost all the variance. In other words, time averaging in that case is essential. So statistics are mainly captured by sampling in time. On the other way around, if MT tends to 0, so My tends to 1, because at the end the sum has to be 1, it means that statistics are mainly captured by sampling in this span-wise direction. And again, we are very happy about these two measures because, as we said, we want something that is very, let's say, easy to implement. And I mean, we have it if we have, let's say, data from turbulent flow simulation. Of course, we can compute the trace of Reynolds stress, and we can compute this average inside MT and inside My. So pretty straightforward to understand from 0 to 1 and capturing in time and in space, and they also very easy to implement. So we of course made some tests, and today I would like to present some of them that are very useful to understand the difference between MT and My and how the computation works. So basically, here are the selected benchmark test cases. So we have the turbulent plane jet flow, and we have the turbulent flow past a cylinder, and we have a turbulent flow past a linear cascade of gas turbine blades. Well, let's start from the turbulent plane jet flow. And we took data from the paper by Professor Klein, Sadiki, and Yannicka. Here I just include the simulation parameters. So we have this distance d equal to 1, u naught 1, it's Reynolds 10,000. And of course, some other details, but most important, we have the, let's say, time window for which statistics were computed. So 22 convective times. Here, we have this figure that displays the trace of the Reynolds stresses obtained from space-time averaging along with the homogeneity indices MT and My. So here we have basically what we defined in the previous slides. And in this specific simulation, it's easy to see that MT basically exceeds My everywhere, suggesting that statistics are mainly captured by sampling in time. But nevertheless, it is evident here that sampling in Y direction plays still an important role in some regions of the computational domain. I don't know if you can see my cursor, my mouse, but well. Another main interest of the present exploration is the relation of the defined indices MT and My with the number of independent samples and SIS. So this number is simply assumed, so of course this is an assumption, as the product of the independent samples in time, NT SIS. Let's see if I can, I think you should see my laser, right? Yeah.
Yes, we can see that, yeah.
Okay, so basically I was saying that this number is assumed as the product of the independent samples in time and TSIS and in the span-wise direction NYSIS. So if NT here, we define it like this. So the minimum between NT and the fraction of time window over the correlation time. So here we have this curly T, which is the total simulation time, and T, which is the number of samples in time. We have this tau conv, which is equal to L11 over the average of U, and LO1 is directional length scale in the axial direction. We took those definitions from Pope book about turbulence. So what does it mean, this NTSIS? So if it is a small number, it means that the number of independent samples is limited by the let's say the number of samples that we have. And if this guy is a big number, then the number of independent samples is limited by this fraction here. And which, of course, it depends on the total duration or the duration of the simulation, because basically this time here is basically the time which is necessary to basically fluctuations are not correlated. And again, basically we have the same thing for NYSIS. So here we have Y, again, the size of the domain Y. Basically, those are the same ideas from the space we applied from the time we are applying to the space. So basically, again, just to recap, if this NTSIS is big, then it means that statistics, like temporal statistics, are the one that plays an important role. Otherwise, let's say we want to play a little more with statistics averaging in the span-wise direction. So in this simulation, here we have the figure for NTSIS and NYSIS, and we see again that NTSIS is always way larger than NYSIS. It means that statistics are, again, mainly dominated by averaging in time. And we were showing that with MT and MY. So basically, it is consistent with the metrics that we already presented, but actually, those MT and MY were much simpler to define and to compute with respect to that. And also because the calculation of the correlation time or distance can be intricate, because we have undershoots, oscillations, bad convergence, and also because we are basically using assumptions that are valid just under, let's say, some let's say assumption. Let's say, for instance, for defining that we need that the flux, for instance, is in equilibrium. So we move now to the second turbulent flow, which is the turbulent flow past a cylinder, and we use their computations from Ferrero, La Rocca, Scovazzi, and Germano from 2021. And here again, some simulation parameters. Here we have Mach infinity equal to 0.2 and Reynolds number equal to 3,900. And we have basically run the, well, no we, but they run the simulation for a time window which is equal to 400 convective times, and the spatial dimension was 3 times the diameters. Here we have the number of ixahedra, since basically it's a DG code, and of course it's not equal to the number of elements and the number of degrees of freedoms per equations. So to evaluate statistical homogeneity in the span-wise direction, the simulation is conducted over basically the full database. So we use T equal to, let's say, 400 convective times. Let's see. Yes, exactly. 400 convective times, and Y equal to 3 times the diameters. But also we want to assess something else, because we want to create 2 sub datasets. So we basically have here one which is 1/4 of the original one, and then we have one which is basically the other way around. So we have 5 convective times, but the entire span-wise dimension. So this is meant because basically in this way, we are, let's say, in the same computational cost. Because one time we applied for time window, one time we applied for the to the space window. So basically, we here comparing the Reynolds stress components R11 at x over d equal to 2.02 using different averaging windows against experimental data. So what we see here is that this case here, which is in blue, closely matches experimental results. And the data set, which is here with the dotted yellow line, actually is far from statistical convergence, and it's highly asymmetric. Well, again, we are having, let's say, an assessment of the statistical convergence, but we see we are putting a lot of effort now. So basically, we are comparing with the experimental data. So that's why we want to apply MT and Y, the metrics that we introduce. So in this case, what we see is that the time averaging is more efficient than span-wise averaging, and the time signal contains significantly more independent samples than the span-wise signal. This is because turbulent structures are primarily advected in this streamwise direction, leading to stronger temporal fluctuations at fixed control stations. And we can see it basically here from this plot, where streamwise fluctuations are much stronger than the span-wise fluctuations. So this is just the physical reason for that. But here we now apply the definition that we defined in the first slides about this new matrix MT and Y. So here homogeneity indices MT and Y are computed, and we see is that again MT is systematically higher than MY, confirming that time averaging captures statistics more efficiently than span-wise averaging. So basically the conclusion here is the same of the previous slide, but for computing this, we spent a lot much more effort than computing MT and then Y. So from that also, from this particular test case, we can kind of propose a strategy for statistically steady flows. So basically, we can make a pattern, let's say. So first of all, we run a preliminary simulation with the minimum span-wise extension required to resolve the largest structures. Then we compute MT and MY to assess the statistical efficiency. And then, okay, we can adjust simulation parameters. So if MT is larger than MY, basically extend simulation time because we want to, let's say, capture statistics with time. But if we notice that MT is basically equal to MY, then we can increase span-wise domain. So this adaptive approach, in a way, will optimize computational cost while ensuring statistical convergence. And now we move to the last benchmark test case, which is the T106C gas turbine linear cascade. And this database was taken from simulation that I run together with Andrea Ferrero and Francesco La Rocca. And here I include some simulation parameters. So we have the M2 IS, meaning the isentropic man number at the outlet, which is 0.65. And then we have the isentropic Reynolds number at the outlet, which is 80,000. And this is just the inlet angle, which is 32.7. And here the parameters of, let's say, the simulation in terms of the database. So we have 20 convective times, and then we have here the spatial dimensions. Again, we are using DG. We have 120 hexahedra, second order, meaning 4,800,000 degrees of freedoms. Again, here in this slide, they reported the trace of Reynolds stress. the trace of Reynolds trace along with the homogeneity indices MT and MY. And again, what we are looking at, it is clear that index MT is larger than MY, consistent with previous observations. So indicating that also in this case, statistics are mainly captured by sampling in time. And in order to assess the influence of computational time on the statistics for the present test case, the trace of, let's say, of the Reynolds traces and the homogeneity indices MT and MY were calculated for progressively smaller time window. You see here we have one convective time, 5 and 10. And as expected, of course, as the computational time decreases, MT index also decreases. However, when compared with MY, it is always remains much higher, the MT, showing that even with a reduced time window, the statistics remain primarily captured by sampling in time. So in the test case considered, time averaging has been proven to be more efficient than spatial averaging. However, we are not so happy about that because time averaging generally requires long wall clock times, which are indicated here with WCT. So what will be, let's say, the possible options? Well, we can extend the domain in a spatially homogeneous direction, or we can try to make ensemble averaging in a way, like, let's say, to have also ensemble averaging, but not fully relying on that. So we make some assumptions for estimating the total computational time. So we say that the flow with temporal and spatial homogeneity in the y direction, so basically is the assumption that we made for all our test case. Then we have the domain dimension, which are indicated as curly x, y, and z. And then we assume that there is a linear scaling of floating point operation with mesh sizes nx, ny, and z. So basically, these are the mesh sizes in each direction. And the total computational time, TCT, in serial execution depends on two factors, which are time to reach a statistical steady state, because of course we have to consider that because before start, let's say, saving our data, we need to reach a statistically steady state. And this guy here, we name it FTI, and then we have the number of flow-through times for collecting statistics, which is FTS. So this total computational time, as we said, for serial execution, it is proportional to the sum of the time to reach a statistical steady state and the number of flow-through times for collecting statistics. How we can, let's say, assume FTS? Well, as NSIS times L squared over curly x times y. So here, L is the characteristic turbulent length scale, and SIS is the number of samples to reach a desired confidence for the statistical error. And knowing that one flow-through time takes for a constant grid spacing nx over CFL times steps, then we can say that this total computational time is proportional to this guy here, which is our first, let's say, term and the second term in this sum. So, as we said, we want to play with the total computational time. We have two possible options. We can extend the domain in a spatially homogeneous direction, or we can make ensemble averaging. So let's try to think about the first one. So we want to extend the domain in a spatially homogeneous direction. So basically, y is increasing here, and y proportionally increases. So basically, it's like this term remains constant. And this term here, we have here ny increases. So extending the domain in a spatial homogeneous direction means that this first term here increases. The other strategy is ensemble averaging. So basically, we suppose that we make capital M simultaneous simulations with capital M times more computational cores. So again, here this second guy remains constant. However, the time to reach a steady state must be achieved for each flow realization. So this in serial increases. So again, we have the same thing as the previous case. So in both cases, as we said, the minimum wall clock time, which is proportional to the total computational time over the number of cores, scales with this guy here. So it is evident that, for instance, we want to, let's say, increase the number of cores, and we also increase the number proportionally, as we said, as an assumption, the number of realizations, so ensemble averages. So still, this guy here is the one that controls all these member here, all this term. And on the other way, if we want to, let's say, increase ny, and also we want to put in our computation more cores in play, in role, then again, it's kind of eliding them. And again, this guy here is controlling and limiting the wall clock time. So it is evident that it is truly important to reduce the time here needed to reach a statistically steady state. So for doing that, of course, it will be possible to explore multi-grid strategies or scientific initial data. This was just, let's say, a discussion, a final discussion that I wanted to share with you. And basically, I am at the end of my presentations. Here are the main conclusions. So basically, we propose a mixed averaging analysis of Reynolds stress in statistically steady turbulent flows, which at least have two homogeneous directions. So this is the hypothesis. But again, these two homogeneous directions can be any. The proposed indices, which are based on the operational decomposition of the total variance, are straightforward and easy to obtain, as we said. And these indices could be used to suggest the best mixed computational strategy in a way, as we discussed for the cylinder benchmark. But of course, we need further research to relate these indices to the conventional statistical convergence methods. So I hope you enjoy my talk, and I really thank you for your attention. And if you are interested in delve into this, let's say, this topic more, you can find this paper that we presented a year ago. So hopefully was interesting for you guys, and I really thank you again for your attention.
Thank you. Actually, you can't see us, but one moment, let me try again. Maybe. Okay, you can see. A moment. Again. Okay, sorry. Can you hear now?
I can hear, but I cannot see you guys.
The webcam is not.
Okay,
Thank you
don't worry.
For your talk. Some question? Any curiosity?
Yeah. Maybe I can also make a question to the audience. I was curious about the background of the audience because of course I wasn't sure about let's say the people that were coming to follow this presentation. I'm just curious.
We are mixed. Yes, like your turn. We are mixed. There are aerospace engineers. Yes, also mathematical engineers, and so also data scientists. So we are mixed. Okay.
Okay. And did you find, let's say, interesting for your backgrounds and for your, let's say, research topics? Did you find, let's say, at least interesting or
For me, sure. For
okay?
me, sure, because yes, I have a background in aerospace, also mathematical, and indeed, since it is quite interesting, I have a curiosity.
Okay.
If I'm not wrong,
Mm-hmm.
tools can be used only when you know that your flow is steady state convergent. Okay, so you
Yes.
must know that your solver is at steady state.
Yes.
Okay, but what happens if one cannot know if the solver has reached the steady state? So your metric.
Yeah, no, but that's a great question. Actually, maybe I was not clear in the assumption, but this is one of the assumptions. So basically, the assumption is that the model, let's say this matrix work for flows that are statistically steady states.
Okay, so you have to know.
Well, sorry, yeah, statistically steady. Yeah.
Okay, so your solver has to be convergent at the end.
Yes.
Okay. And so, okay, and yes, I was wondering just this.
Okay.
And curiosity, you mentioned that you have used a discontinuous gradient scheme
Yes.
for the turbine. Yes.
Yes.
Okay. Why you have used a second order scheme?
That's a good question. You mean you have a DG solver, why you don't go high with order?
Yes.
Well, that's a good question. The reason of that is also, uh, let's say, it was at that time we wanted to assess uh, the the feasibility of this approach with MT and MY. And basically, we wanted to have a simulation that was, let's say, easy to compute in time, meaning that it was light in terms of database, in terms of
Also stability.
yeah, kind of yes, and also yeah. Basically, we were not very interested at the moment in which we were saving the database about the order of the DG because we were more interested in, let's say, uh, in the post-processing
Okay.
method that we were trying to prove. So basically, this is just let's say um, time manage time management, like just not let's say scientific reason for that. Of course, it's my in the previous, in one of the first slides I said, okay, here this talk today will focus on the second part, so on the statistical operator. So basically we assume that we have already data. We don't care about how we compute it because for the purpose of this, let's say, of this procedure, we wanted just to assess the post-processing part. So this is the reason. I've known if it was so, uh, let's say,
Okay, there is a question from my supervisor. My supervisor. Okay. So if you cannot see me, can you hear me right?
sorry, I'm not hearing clearly the voice.
That's fine. Okay, so now
Can you try it again?
can you hear me now?
Yes.
Okay, so yeah, since you cannot see me, I'm Nicola Torricello. First of all, yeah, thanks for the presentation. It's
kind of a specific topic, but it's at the same time very fundamental, I would say, inside of, let's say, the topic of turbulence. So I appreciate it. It's kind of related to, I mean, the choice of doing second order DG. Maybe I can help out at the beginning, meaning that I saw, I mean, the last simulation, it's considered an implicit AJS, right? So you're not,
Exactly.
I mean, yeah, so you want to, I mean, it's good to have some stabilization, I guess, not doing a super high order that you might have some troubles. And related to that, did you investigate a little bit what happens with resolution? I mean, I do like to studying these indices from the range, let's say, of coarse LES to almost DNS levels. If you expect something different,
Well, that's a very interesting question, and actually, your suggestion is, let's say, very valuable. I mean, it's something that we can try to do that for sure. We didn't do it, but it's a way to assess if basically, let's say, accuracy of data that we have are changing something in this post-processing procedure. But yeah, we didn't do that.
yeah, I mean, like if it's, it would be reasonable to think that for LES, maybe, I don't know, like in the span-wise directions, structures are more dissipated, and it's like it's even more important than averaging, or vice versa. This type of things, like if it,
Yes. You know, yeah, it was very clear your question, and actually is a very interesting question, and yeah, I think it's a very good suggestion. So yeah, we can, yeah, we can try. Actually, it's very, let's say that this method can be applied by any solvers, meaning that if you have database, you can try, and of course you have at least two homogeneous direction, you can try to basically build this matrix and see what happens. Of course, it's as one point that we want to stress is they are very easy to implement. So basically, yeah, if you have a database, so and if you want to try them, let me know. I'm curious as well.
yeah, I guess that like low Reynolds number channel flows, you can play around with resolution as much as you want, and you can build something like that. So yeah, that would be interesting. Okay,
Yeah.
thank you very
Oh,
much.
thank you. Actually, thank you to you.
Any other curiosity? Also from online, don't be shy. Okay, let's thank again Michele.
It was a great pleasure to join you, and hopefully this was, let's say, just a way to keep in touch. So maybe if you want to just have a discussion later on for other similar topics, because as I said during my PhD, I did this post-processing part, but also about DG. I'm very happy to discuss about, you know, like similarities in these research paths that we had. So maybe we can do it offline in another, let's say, place.
Yes, sure. Thank you very much. Thank you.
Thank you. Bye.
Bye. Bye.